Hydrogen as a coolant. Some issues. The issues are design and operation. And for operation, sub-issues are seal oil system, drying, purging and makeup. The design issue. The use of gaseous hydrogen as a coolant is based on its properties, namely low density, high specific heat and the highest thermal conductivity of all gases. It is 7 to 10 times better at cooling than air. Another advantage of hydrogen is its easy detection by hydrogen sensors. A hydrogen-cooled generator can be significantly smaller and therefore less expensive than an air-cooled one. For stator cooling, water can be used. For the highest power generators up to 1800 megawatt, hydrogen and water cooling is used. The rotor is hydrogen cooled while the stator windings are made of hollow copper tubes cooled by water circulating through them. Hydrogen gas is circulated in a closed loop to remove heat from the active parts. Then it is cooled by gas to water heat exchangers on the stator frame. Request. It is hoped that this session is going to be useful to you. Please press like button. Please सब्सक्राइब दिस चैनल. बहुत जल्दी यह लेक्चर आपको हिंदी में भी उपलब्ध होगा. An online thermal conductivity detector analyzer is used with 3 measuring ranges. The first range, 80 to 100% hydrogen, is to monitor the hydrogen purity during normal operation. The second, 0 to 100% hydrogen, and third, 0 to 100% CO2 measuring ranges allow safe opening of the turbines for maintenance. Hydrogen has very low viscosity, a favorable property for reducing drag losses in the rotor. These losses can be significant due to the rotor's high rotational speed. A reduction in the purity of the hydrogen coolant increases windage losses in the turbine due to the associated increase in viscosity and drag. A drop in hydrogen purity from 98% to 95% in a large generator can increase windage losses by 32%. Windage losses also increase heat loss in the generator and increase the problem of dealing with the waste heat. The operation issue. Seal oil system. The bearings have to be leak tight. A hermetic seal Usually a liquid seal is employed. Turbine oil at pressure higher than the hydrogen inside is typically used. A metal, for example brass, ring is pressed by springs onto the generator shaft. The oil is forced under pressure between the ring and the shaft. Part of the oil flows into the hydrogen side of the generator, another part to the air side. The oil entrains a small amount of air as the oil is recirculated. Some of the air is carried over into the generator. This causes a gradual air contamination buildup and requires maintaining hydrogen purity. Scavenging systems are used for this purpose. Gas is collected in the holding tank for the sealing oil and released into the atmosphere. The hydrogen losses have to be replenished either from gas cylinders or from on-site hydrogen generators. Degradation of bearings leads to higher oil leaks, which increases the amount of air transferred into the generator. Increased oil consumption can be detected by a flow meter for each bearings. Operation Sub-issue drying. Presence of water in hydrogen has to be avoided as it causes deterioration of hydrogen's cooling properties, corrosion of the generator parts, and arcing in the high voltage windings, and reduces the lifetime of the generator. A desiccant based dryer is usually included in the gas circulation loop, typically with a moisture probe in the dryer's outlet, sometimes also in its inlet. Presence of moisture is also indirect evidence of air leaking into the generator compartment. Another option is optimizing the hydrogen scavenging so the dew point is kept within the generator's specifications. The water is usually introduced into the generator atmosphere as an impurity in the turbine oil. Another route is via leaks in water cooling systems. Operation Sub-issue purging. The flammability limits 4 to 75% of hydrogen in air at normal temperature, wider at higher temperatures. Its auto ignition temperature at 571 degrees centigrade, its very low minimum ignition energy, and its tendency to form explosive mixtures with air require provisions to be made for maintaining the hydrogen content within the generator above the upper or below the lower flammability limit at all times, and other hydrogen safety measures. When the generator is filled with hydrogen, overpressure has to be maintained as inflow of air into the generator could cause a dangerous explosion in its confined space. The generator enclosure is purged before opening it for maintenance and before refilling the generator with hydrogen. During shutdown, hydrogen is purged by an inert gas and then the inert gas is replaced by air. The opposite sequence is used before startup. Carbon dioxide or nitrogen can be used for this purpose as they do not form combustible mixtures with hydrogen and are inexpensive. Gas purity sensors are used to indicate the end of the purging cycle, which shortens the start up and shutdown times and reduce consumption of the purging gas. Carbon dioxide is favored as due to the very high density difference it easily displaces the hydrogen. The carbon dioxide is admitted to the bottom of the generator first, pushing the hydrogen out at the top. Then air is admitted to the top, pushing the carbon dioxide out at the bottom. Purging is best done with the generator stopped. If it is done during slow speed unloaded rotation, the generator fans will mix the gases, greatly increasing the time required to achieve purity. Some gaseous hydrogen has to be kept for refilling the generator, but it can also be generated on site. Hydrogen is often produced on site using a plant consisting of an array of electrolysis cells, compressors, and storage vessels. This reduces the need for storing compressed hydrogen and allows storage in lower pressure tanks with associated safety benefits and lower costs. Request: it is hoped that this session was useful to you. Please press like button. प्लीज़ सब्सक्राइब दिस चैनल। बहुत जल्दी यह लेक्चर आपको हिंदी में भी उपलब्ध किया जाएगा।